Hi everyone, in this video I'm going to go through the midterm review homework. It looks like this. There are 16 questions, should be shared on your classroom. So before you get started, you should have with you a periodic table, polyatomic ions list, and the heat formulas and constants, because this is what you're going to be given for the midterm, so you want to have this familiar. Okay, let's start. Question 1. A vat of molten liquid iron at 2000 degrees Celsius is cooled down to room temperature. The melting point of iron is 1538 degrees Celsius. Draw LOLs for this. So, basically, you always want to start with a 5-point heating curve. So, up, flat, up, up. All right. So it tells us we're at 2000 degrees. And it tells you it starts out molten or liquid. So let's just assume we're starting right around here. The melting point is 1538, and it's going to cool down to room temperature. So we'll call this about 25 degrees Celsius. So it's going to cool down to 1538, then it's going to freeze, then it's going to cool all the way down to room temperature. So starting point, ending point. So I can tell this is going to be a 3-step process. So if you did a quantitative problem, you do 3 steps. For LOLs, 3 steps. So let me try to squeeze them all in here. Actually, I'll do it on a new page so it's not all crammed. So LOL, that's the first step, second step, third step. Okay, you put your system in the O. Now this is iron, right? It's iron. Yeah, so iron is Fe, so I'm going to put the Fe inside here just to show that we're looking from the perspective of the iron. And let's put our starting and ending conditions. So we start with 2000 degree liquid. So 2000 degrees Celsius liquid, and that's going to cool down until it hits its melting point, or I should say freezing point, which is 1538. So it's going to turn into 1538 degrees Celsius liquid. Remember, it's not going to freeze in one step. It's going to cool down to the freezing point, then it's going to freeze. So here's the actual freezing process. So we're going from 1538 degrees Celsius, is that right? Yeah. Liquid to 1538 degrees Celsius solid. And now that it's solid at 1538, now it can cool down to room temperature. So 1538 degrees Celsius solid down to 25 degrees Celsius solid. Okay. ETH, EPH. Remember, we're just cooling it down. There's no chemical change happening here, so no ECH is needed. ETH, EPH. Okay, now I generally only write it once. Your teacher might want you to write it for all 3 of these. For the bars, we start with liquid and liquid, so phase is going to get 2 bars and 2 bars. For thermal, this is your judgment call. Now, I usually use for water 0 degrees is 1, room temperature is 2, and 100 degrees is 3. Now, if you scale that up to this, we'd have like 50 bars. So the best thing to do is kind of keep it relative. If this is going to freeze at this, let's call that 1 bar. That's the freezing point of iron. So that's 1 bar. So let's call this 2 bars. It has a little bit more heat than freezing point, and it's going to cool down to freezing point. 4 and 3, the difference is 1. And that block is going which way? Well, it's cooling down, and notice the iron had 4, now it has 3. It has to go out. So that's going to be exothermic. Okay, here we're starting at 1538 liquid, so let's do my phase energy, which is 2 bars for liquid. It's cooling, it's not cooling down, it's freezing into solid, so that's going to be 1 bar here. And notice the temperature is the same. So I want to be consistent, 1 block for 1538 and 1 block for 1538. So you're going from 3 to 2, a difference of 1, and that 1 is leaving. And finally, 1538 solid down here, that's 1 block of phase, and it's still solid, 1 block of phase. We did 1 block for 1538. Let's do a tiny little sliver fraction of a block for 25. So the difference is your little sliver of a block, and that's also going out. So a couple things to check with LOLs. First of all, this should match that, which it does. This should match that, which it does. All 3 of your arrows should always be pointing in the same way, and we can write, if we have space anywhere, exothermic, because heat is leaving. Okay, so that's question 1. Question 2, how much energy is given off by a 450 gram sample of water as it cools from 81 to 29. So this is going to be a quantitative heat problem. First of all, you want to do a 5-step heating curve. Up, flat, up, flat, up. So we're starting at 81 degree water. That's liquid. We're ending at 29 degree water. Still liquid. So nice and easy. 1-step process. All that's happening is it's cooling down. It's not freezing. It's not boiling. Anything like that. So according to your heat formulas worksheet, Q equals mc2 delta T. That's the equation for region C. So we just plug it all in. Mass is 450 grams. C2 is 4.18 joules per gram degree Celsius. And your delta T is your change in temperature. 81 minus 29 is 52. Okay. Gram cancels gram, degree Celsius cancels degree Celsius. I'm left with joules. Does that make sense for energy? Yes, it does. So 450 times 4.18 times 52. For sig figs, look at the numbers you used. 2 sig figs, 3 sig figs, 2 sig figs. I'm going to use 2 sig figs, so I'm going to call this answer 98,000. 98,000 joules. Okay. All right, next. What's a percent composition of calcium hydroxide? So when I say percent composition, I'm looking for percent composition by mass. What's the mass breakdown of all those elements? Well, first thing we have to do is name this correctly. So calcium is Ca2+, hydroxide is OH-. You crisscross them, you're going to need 1 calcium and 2 hydroxides. So CaOH2. Now, for the percent composition, you want to get the entire molar mass of this and then compare each one to that. So for CaOH2, there's 1 calcium, that's 40.08, plus 2 oxygens, that's 32, 16 plus 16, plus 2 hydrogens, that's 1.008 times 2. I get 74.096. I'm going to call that 74.10 grams per mole. Okay, your teacher will probably agree rounding off to 2 decimal places is totally fine for these. Okay, so that's the total mass, and now we need to see what each element is. So for calcium, it's only 1 atom in this formula unit. So it's just going to be 1 calcium, which is 40.08, divided by the total, 74.10. 40.08 divided by that answer gives me 0.5409. Now looking at sig figs, I see 4 and 4. I'm going to go with 54.09% calcium. For oxygen, notice how many O's are there? 2. 2 O's because there are 2 hydroxides. Each hydroxide is 1 O. So I'm not going to say 16.00. I'm going to say 32.00 because there's 2 O's. 32.00 divided by 74.10. You do the math and you get 74.10. 0.4318, which I'm going to call 43.18% oxygen. And finally for hydrogen, there are 2 hydrogens in here. Each hydrogen is 1.008 times 2 gives me 2.016. Divided by my same total, 74.10, gives me, I gotta be careful here, it's 0.02721. I'm gonna shift it twice, call it 2.721%. 4 sig figs for all of these, and that's percent nitrogen. Okay? So if you do it right, it should add up to 100. So if you have a minute, take it, add it up to 100. Let me just check my answer key real quick. Yep. Okay. Next question. 5.0 liter sample of gas has a pressure of 2251 torr at 821 degrees Celsius. I can already tell, combined gas law problem. In an attempt to ease the pressure, the temperature is decreased to 419 and the volume is doubled. So we're attacking it both ways. Remember, when you cool a gas down, the particles slow down, so they exert less pressure on the walls. And And when you increase the volume, there are more surface area, so the pressure on those walls is also going to be down. So the pressure should go down. What's the new pressure of the gas? Okay, let's write what we have here. So this is the initial volume, V1, 5.0 liters. Pressure 1, P1, equals 2251 torr. Now, do you have to convert that to ATM? No. The problem doesn't specify. It doesn't say what's the new pressure of the gas in ATM or MMHG. So whatever you plug in is fine. The only unit you have to plug in is Celsius. Sorry, Kelvin, not Celsius. So T1, 821 degrees Celsius. We have to turn that to Kelvin in order to use this gas law. So 821 plus 273, 0.15. The 0.15 cancel out anyway. So that's going to be 1094 Kelvin. Okay. So in an attempt to ease, okay, the pressure's decreased, the temperature's decreased. So 419 is the new Celsius temperature. So 419 plus 273 gives me 692 is T2. And that's Kelvin. And the volume is doubled. So it was 5.0. We're going to double that. Technically with 2 sig figs, it's going to be 10 point. V2 equals 10 point liters. We're looking for the new pressure. So P1 V1 over T1 equals P2 V2 over T2. In order to get, what are we looking for? P2, new pressure. So multiply both sides by T2. T2 is going to reappear up here and disappear from here. Now again, we want P2 by itself. Divide both sides by V2. And there's our formula. Okay, so let's plug everything in. T2, 629 Kelvin. P1, 2251 torr. V1, 5.0 liters. V2, 10 point liters. T1, 1094 Kelvin. Notice it didn't say anything about number of particles, so we have to assume that that's held constant. Remember, in order for this to be a correct formula, it has to be held constant. Okay, let's check our units. Kelvin cancels Kelvin, liter cancels liter. We're left with torr. Does that make sense for pressure? Yes, it does. Caught myself. 692, 629. That should be 692. 692 times 2251 equals, times 5 equals, divided by 10 equals, divided by 1094 equals, and let's talk sig figs here. Look at the numbers you used. I'm seeing 3, 4, 2, 2, 4, 2 sig figs. So my calculator says 711. I'm going to call that 710. 710 and my unit is torr. Now it's always worth taking a second. Does that make sense? I think it does, because notice my pressure, my volume doubled, which means the pressure should go down by half, and my temperature went from 821 to 419, which is not quite going to half, but it's close. So again, it went down by about another half. So down by half and down by another half, it's about 4 times down, and we're close. So yes, this makes sense. Okay, next problem. We don't have time, 13. All right, molar mass of neon is 20.18 grams per mole. What's the mass of one single neon atom? This is basically just a conversion factor problem. It's one of these grams to moles to number of particles. So just to clarify, grams to moles to number of particles. The moles are always the middleman. I'm looking for the mass of one particle. That's the mass of one particle. You can't do that in one shot. Moles is always the middleman. To go from grams to moles, we use the periodic table, molar masses. To go from moles to number of particles, we use Avogadro's number. So we're going to have to use both for this. So you want to set up your starting point. We're looking to get mass. Grams is what we're looking to find. What are we starting with? One single neon atom. So, one atom. That's our starting point. We need to turn this into moles. Times 1 mole divided by 6.022 times 10 to the 23rd atoms. Okay, 1 atom cancels this many atoms. Notice if you did the math on this, I mean, it's basically 1 over that number. It's going to be a tiny, tiny, tiny number. And that makes sense. If you have 1 atom, how many moles is that? That's like a tiny fraction of a mole. We're not done yet. We need to go from moles to grams. Now that's where this comes in. That's your molar mass. So we can set this up as a fraction. You can either say 20.18 grams over 1 mole, or 1 mole over 20.18 grams. What makes sense? Well, mole has to cancel mole, so let's put that down here. 20.18 grams on top, and you work it out. If you set it up like this, you're never going to have to question, oh, should I multiply by the molar mass? Should I divide by the molar mass? You'll always know, because it always is going to cancel out properly. Okay, 1 times 1 you don't need to do. Divided by, I'm going to use the e function so I don't mess up. If you don't use e, use your parentheses, but you should use e. Divided by 6.022 E23 equals times 20.18 equals, and my answer, now sig figs are tricky on this. Technically, since I'm really asking for just 1, I really should use 1 sig fig, so I'm going to go with that. I got 3.35, but I'm going to just say 3 times 10 to the negative 23rd grams. Now, does that make sense? Yeah, because 1 atom's obviously going to have a tiny, tiny, tiny mass, so that makes sense. Okay. All right, number 6. 125 gram sample of 80 okay, so it looks like another quantitative heat problem. All right. 5-step curve. 1, 2, 3, 4, 5. All right, we're starting with 80-degree water. That's going to be here. 4/5 of the way up the liquid heating curve. What's the final temperature of the water gas? I think on your sheet it says water vapor. I realize now if it's above the boiling point, it's called gas, not vapor. So it's going to end up somewhere up here, based on the phrasing of the question. Where exactly, I don't know. That's for us to figure out. But based on the phrasing, it's going to make it to the boiling point, and it's going to totally boil, and then it's going to heat up more. Because if it didn't, I wouldn't ask it this way. So this is one of those problems where you're going to need to see how much energy you have left. Basically, you're giving it one giant lump sum of energy, 312,000 joules, and that energy has to do 2 things before it can start heating up that gas. First, it has to take the water up to 100. Then it has to boil all of it away. Once it's done with that, you're only going to have a little bit of energy left. That little bit of energy is what's going to actually heat that up. So you have to figure out how much of it is left over. So the first thing we do is say, how much of this 312,000 is used up just going from 80 to 100? We're going to use Q equals mc2 delta T, and you're going to solve for Q here. A lot of people mess this up. They say, well, look, you're given Q, just plug that in. Well, if you plug this in, and you plug that in, and you plug your degrees in, it's nothing to solve for. So we're not going to plug this in. We're going to find Q, which tells us how many of these are used just to heat it up. So Q equals 125 grams times C2, which is 4.18 joules per gram degree Celsius. And delta T, change in temperature. It's starting at 80 point. It's going to go to 100. So it's a 20 point degree Celsius difference. Let's see what we get. 125 times 4.18 times 20. 10,450. We'll deal with sig figs at the end. So what that means is that's how many joules are needed just to heat this hot water up to 100. We're going to subtract this from that to see how many are left over. So 312,000 minus that answer gives me 301,550 joules left. And I like to write that. 301,550 joules left. Left to do what? Well, now they have to boil that water. Q equals mLV. So you just plug in your mass, which is 125 grams. Remember, LV can also be HV. They mean the exact same thing. 125 grams times the latent heat of vaporization. I use 2260. Your teacher might use something slightly different, and that's joules per gram. Gram cancels gram. Let's see what we get. 282,500. Notice that's like the bulk of the energy. Boiling water takes tons of energy relative to heating it up and even melting it. So that's how much we had left. this much is used just to boil it. Notice we're not going to have that much left over. So 301,550 minus my answer here tells me that after all of that, I only have 19,050 joules left. And now we're ready to start heating up that water. So now we're going to see how hot we can get that, I shouldn't say water, that water gas. How hot can we get that gaseous water? So, let me get a new slide here. We're in region E, as I call it. Q equals mc3 delta T. Q equals my mass is still 125 grams. Well, technically some of it's going to evaporate away. Well, you're trapping it, of course. I guess that makes sense. C3 is the gas constant. I use 1.90 joules per gram degree Celsius. Your teacher might use something slightly different. And delta T, that is what we're solving for. In fact, I normally set this up differently. I should have rearranged first. I could do it this way. Q, we're actually going to plug in Q now. This is how much energy we have left over, 19,050 joules. Okay. Now, normally I do arrange this differently so the units cancel out. Since I already wrote it out, I'm just going to solve it. So, let's see, to get that by itself, we're going to divide both sides by this and this. Notice we divide both sides by both of these and they're going to go away. And in fact, if I do that, I can see the units. Joules are on top here. If I divide by this, joules cancel. I'm also going to divide by this, so gram and gram cancel. You're left with just degrees Celsius as that like double denominator. It's going to come up to the top. So 19,050 divided by 125 equals, divided by 1.90 equals, and my answer is 80.21. Now we can look at our sig figs here. So looking back at the original problem, I'm seeing 80 point as kind of my limiting factor for sig figs. I'm going to go 2 sig figs because technically my first delta T was 20 point. So that's going to mean 80 point is my temperature change, delta T. But that's not my final answer. The final answer doesn't say how much it's going to change by. It says what's going to be the final temperature. Well, that water gas started at 100, and it's going to heat up by 80. So my final answer, when we add, we don't do decimal places. We don't do sig figs. We do decimal places. It's going to be 180 degrees Celsius. Our final answer. Okay. Yeah. Probably if you said 180 without that for 2 sig figs, that would probably be acceptable too. Okay, question 7. Hydrogen gas inside a rigid steel box is heated from 42 to 93. All right. So another combined gas law problem. We're again solving for P2. All right. So when I say rigid steel box, that's a pretty clear clue that volume is going to be held constant. In fact, you don't see any mention of volume, so volume has to be held constant. And what else is held constant? Moles, or number of particles, because you don't see anything here. So let's write what we're given. So it's going from 42 to 93 Celsius, but remember, you can't plug Celsius in, you have to plug Kelvin. So T1 is 42 degrees. We're going to add 273.15. The 0.15 is going to cancel anyway, so we just add 273. 315 Kelvin. T2, 93 plus 273, 366. Okay, this is important. It looks like if you came into this class, you might say that temperature more than doubled. It didn't. Remember, in terms of the true absolute temperature scale, it didn't double. It went up by 10 or 15%. Okay, the original pressure was 1.00 atm. That's P1. We're looking for P2. So P1 V1 over T1 equals P2 V2 over T2. Notice there's no mention of a volume change at all, so I'm just going to erase V1 and V2, just like I'm not going to include N1 and N2 here either. So let's get P2 by itself. Easy enough. We just multiply both sides by T2. That's going to reappear up here. And that's my formula. So P2 equals P1, which is 1.00 atm, times T2, which is 366 Kelvin, divided by T1, which is 315 Kelvin. Kelvin cancels Kelvin. We're left with atm, which makes sense. So 366 divided by 315 gives me a final answer. Now for sig figs, I'm seeing tricky. 2 sig figs, but did I plug in 42 or 93? No, I plugged in the Kelvin. So you look at these numbers that you actually used, and I'm going to go with 3 sig figs because of this. 1.16 ATM. Okay. It's always worth asking yourself, does that make sense? Well, first of all, we're heating the gas up. Does it make sense pressure's going to go up? Yeah, of course. It's a fixed container. You're heating it up, pressure's going to increase because, of course, the particles are moving faster, so they're smashing the walls harder. Does it make sense it went up by this much? Yeah. Because again, if you just looked at these numbers, you might say, hey, the pressure's going to double because it's going from 42 to 93. But it's not. It's only going from 315 to 366, which I said earlier is about a 15% change. Well, it looks like it's about a 16% change. So that's how much it went up by. So it makes sense. Question. Oh, why is this frozen on me now? Let me see if I can reopen this. Open. Midterm review, homework questions. Okay, why? Okay, that's not good. Let me close this out. All right. Smart notebook. All right, I believe that it will be here. Question 8. Empirical molecular. A certain type of sugar is found to contain this percent carbon, hydrogen, oxygen. What's the empirical formula? If the molecular weight is 180, what's the molecular? Now these are two separate questions. Let's hold off on the molecular formula because in order to solve that, you need the empirical. So let's get the empirical first. Now the empirical formula is always the simplest ratio of elements, but you can't base it off of the mass or the percent composition. You have to base it off moles. Now if I give you grams, you're going to turn all of those grams into moles and compare them. But in this case, I didn't give you grams. I gave you percentages. So if I give you percent, what you want to do is assume it's a 100-gram sample. So if it's 100 grams and 40% is carbon, that means 40 grams would be carbon. So we can just make that assumption because all we need is the right proportions. So let's just say 40.0 grams of carbon, 6.71 grams of hydrogen, and 53.3 grams of oxygen. We have to turn all of these into moles. Times 1 mole over 12.01 grams. That's carbon's molar mass. Hydrogen's molar mass is 1.008 grams. And oxygen, I call it 16.00. All right, let's do the math. Make sure that's still working there. Okay. So 40 divided by 12.01 gives me 3.33 moles of carbon. I like that number, nice and clean. 6.71 divided by 1.008 gives me 6.66 moles of hydrogen. I like what I see so far. Look at that beautiful, nice, clean mole ratio there. And 53.3 divided by 16, beautiful, 3.33 moles of O. So, if you recognize the ratio, you could just write it down. If not, you take the smallest number and divide each of them by that. So let's pretend you can't see, in this case, the 1 to 2 to 1 ratio. Well, this is the smallest number, as is this. Divide both of them by 3.33, or all three of them. And what you're essentially doing by dividing by the smallest number is you're forcing it to be a something to 1 ratio. Or in this case, it's going to now be a 2.00 to 1 to 1 ratio. So it's very obvious now. So this ends up being 1.00 moles of carbon. This ends up being 2.00 moles of hydrogen. This divided by this is 2. And this is 1.00 moles of oxygen. So it's going to be CH2O. That's your empirical formula. Now, molecular formula. So in order to find the molecular formula, the first thing you need is your empirical formula. Then you also need to look in the problem and find the molar mass, also known as molecular weight. So it says it's 180 grams per mole. So what you do is you find the molar mass of your empirical formula, and then you compare it to that. So CH2O, one carbon is 12.01, two hydrogens is 1.008 times 2, and oxygen is 16. I add them up, I get 30.03. That's very close to 30, and I could already tell what it's going to end up being. So that's basically, we call it 30.0 grams per mole. What we then do is compare these two numbers, and I can see the obvious ratio now, but generally what you want to do is divide your molar mass from the problem by the molar mass of your empirical formula. It's always going to be the bigger one divided by the smaller one, or they could actually be equal if the two are actually equal. So again, bigger divided by smaller, or if they're equal, it's 1 to 1. So in this case, 180 divided by 30 is 6. What does that 6 tell you? It's like the multiplier. It means that the actual formula is 6 times heavier than the molar mass of this. Or in other words, the true formula is 6 times heavier than CH2O, but it's still in the same proportion. So what you do is you apply that 6 to all of these numbers. So C1 becomes C6, H2 becomes H12, O1 becomes O6. C6H12O6, that's our good friend glucose from back in bio. So that's our molecular formula. Question 9. Draw LOLs to represent, this is going to be a long problem. Okay, so how are we doing on time? For this one, I don't feel the need to go through the entire thing. If you have questions, you can ask your teacher, or you can check the online answer key for that. But I will just show how many steps it's going to be. Up, flat, up, flat, up. We're starting with 130 degree water gas, so here's our starting point. We're ending with 0.0 degrees Celsius ice. Now this is ice, but we're ending here. Notice, we're technically ice, but we're actually at the brink between these two. So this is going to be a 1, 2, 3, 4-step problem where you go from 130 gas to 100 gas, 100 gas to 100 liquid, 100 liquid to 0 liquid, 0 liquid to 0 solid. 4 steps. So you should have 4 LOLs. Question 10. How much energy? So this is going to be a quantitative heat problem. How much energy is absorbed by a 10-kilogram block? All right. Up, flat, up, flat, up. So it's going from -6 to -12. Negative 12 to -6. So it's just going like that. It's a one-step problem. One-step problem. Okay, so the formula down there, Q equals mc1 delta T. We're looking for heat, so this should be pretty simple. The mass is 10 kilograms, but I cannot plug in 10 for mass. It has to be in grams. Why? Because the C value we use is calibrated on grams. So you have to use grams for this. So if you can't do this in your head, which you should be able to do, it's 10,000, you could say 10 grams times kilograms, it's that's kilograms. So for kilograms, it's 1,000 grams equals 1 kilogram. So that's what your setup looks like. 10 times 1,000 is 10,000. So Q equals 10,000 grams times C1, which I use 2.10. Your teacher might use something slightly different. And your delta T, 12 to 6.0, let's go with 6 degrees. So 6 degrees Celsius. I prefer to keep this, oh no, it would be positive either way because you're heating it up. All right, let's see what we get. 10,000 times 2.10 equals, times 6 equals 126,000. Now in terms of sig figs, this one's actually tricky. Even though it looks like when I made the problem, I tried to get it to be 2 sig figs. If we really want to be careful with the problem, the difference, the delta T here, is -12 minus -6, or -12 plus 6.0. But we round off to decimal places, not sig figs. So really it should be 1 sig fig. So if you're going by 1 sig fig, you're going to call this 100,000. If you're going with 2 sig figs, you're going to call it 130,000. And we generally are a little less strict on sig figs for these quantitative heat problems. So really either one would be acceptable. But confirm that with your teacher. Question 11. What's the percent composition of aluminum sulfate? Okay, so this is kind of 2 problems in one. Question 1. Do you know the formula for aluminum sulfate? Very important that you know your naming. Well, aluminum sulfate is going to be ionic. You know that because aluminum is a metal and because sulfate's a polyatomic. So we write aluminum with a 3+ charge. We write sulfate, SO4 with a 2- charge. You crisscross the charges. The 3 is going to go with the sulfate. The 2 is going to go with the aluminum. So we have Al2, and now we need to show 3 sulfates, so you need parentheses. Like that. Okay, so for percent composition, we have to first find the percent comp of the molar mass of the entire thing. So 2 aluminums is going to be 26.98 times 2. How many sulfurs are here? 3. So 3 sulfurs, 32.066 times 3 gives me, I'm just adding it all up as I go. And then I'm going to add how many oxygens? 12. 12 times 16. So my total molar mass ends up being 342.16. I usually round them off to 2 decimal places. Okay? Let me check my answer key to see if I got that correct at least. Let's see. Yeah. Okay. So percent composition. I need my percent aluminum. So I have 2 aluminum atoms in this formula unit. So it's going to be, I have it saved in my calculator. 26.98 times 2 is 53.96 grams of aluminum divided by my total mass, 342.16 grams. Let's work that out. Ooh, messed that up. Hold on. 53.96 divided by 342.16 gives me, well, you move the decimal point twice, and with 4 sig figs, 15.77% aluminum. All right. Next, sulfur. I have 3 sulfur atoms inside that formula unit. So you're going to go sulfur times 3. Well, sulfur times 3, 32.066 times 3 is 96.198. 96.198 divided by the same total mass, divided by 342.16. Move the decimal point twice, 28.11% sulfur. And for oxygen, I'll do it over here. I have 12 oxygens. 12 times 16 is 192. 192 divided by my total mass of 342.16 gives me, move the decimal twice, 56.11. Okay, so my final answer, you would report these 3 percentages. And again, you want to check, does that equal 100%? Looks pretty good to me, because I notice 11, 11, 77, that's 99, which is close to 100, and then the other numbers seem to work that way. Okay, so that's my answer. Question 12. Hot air balloon occupies 13,000 liters on the ground. What volume? Okay, so this is going to be a combined gas law problem. So let's write what we're given. So my V1 initial volume is 13,000 liters. My initial temperature, T1, is 19 degrees Celsius. You add 273 to that, 292. I don't trust myself. I've made so many mistakes. Yes, 292 Kelvin. And let's see. What else are we given? Assume constant pressure. Well, that was awfully generous of me because, of course, in real life, that's not going to be true. Pressure is going to drop as you rise. But let's assume constant pressure. Okay, and no air can go in or out. What am I hinting at here? No change in moles. N is constant. So V1, T1 are given. I'm looking for what's the new volume where the air temperature is negative 12. So T2 equals negative 12 degrees Celsius. So 273 minus 12 gives me 261 Kelvin. And I'm looking to find the new volume. So P1 V1 over T1 equals P2 V2 over T2. Notice I didn't even include N1 and 2 because moles are constant. I can also get rid of pressure because according to this problem, not in real life, pressure is constant as you rise, which of course it isn't. Pressure would drop. Let's see, we're solving for V2. So to get V2 by itself, T2 just reappears up here. All right. So V2 is going to equal T2, which is 261 Kelvin, times V1, which is 13,000 liters, divided by T1, which is 292 Kelvin. Kelvin cancels Kelvin, liters are left, that makes sense. So 261 times 13,000 equals, divided by 292 equals, and looking at sig figs, 2 sig figs, 3 sig figs, 3 sig figs. I'm going to go 2 sig figs in my answer, 12,000. My unit is liters. And again, it's worth taking a think about this. Does it make sense that my volume dropped by about 1,000? Well, the temperature went from 19 to negative 12, so that's a slight drop in temperature. Look, it went from this to that. Slight drop in temperature, so the volume should drop slightly. Yes, it makes sense. Question 13. How many atoms are in a 2.90 kilogram sample of pure water? Tricky question, because water, I'm asking atoms, not molecules. All right, so this is going to be another one of those grams to moles to number of particles problems. But in this case, oh yeah, it's not grams, it's kilograms. So again, grams to moles to number of particles, I'll just call that N. Okay, and these can of course go backwards. So I'm starting with 2.90 kilograms of water. I'm going to call that H2O. Now the first thing I have to do is get this out of kilograms. Anytime you do these types of conversions, you need to use grams because that's what the periodic table is based on. So this, you're going to multiply it by 1,000 grams per kilogram, and right off the bat, kilograms of water become grams of water. Now that we have grams, we need to go from grams to moles. How do we do that? Periodic table. You look at the molar masses. Now for water, I've done this enough, I have this one memorized, but you do 2 H's and 1 O, add them together, you get 18.02. Now, where is that going to go? Okay. 1 mole of water equals 18.02 grams of water. Okay, that's the molar mass. This many grams equals 1 mole. So I can go 1 mole divided by that, or I can go that divided by 1 mole. Grams need to cancel and turn into moles here, so I'm going to put my grams on the bottom and my 1 mole on the top. And notice now my grams cancel my grams, and I'm left with moles. Do this, you will not make errors in this case. Okay? Instead of just memorizing when do you multiply it, when do you divide it, work it out as a conversion factor and you won't make mistakes. Okay? But I'm not asking for how many grams, or how many moles of water there are. I'm asking how many atoms. So I need to go to number of particles. So I'm going to use Avogadro's number, but here's the tricky part. I told you the mass of water. That tells you, using Avogadro's number is going to give us the molecules of water, because it's that many, I mean, that's basically the molar mass. 18.02 is a molecule of water, not an atom of water. So I'm going to multiply this by 6.022 times 10 to the 23rd molecules of H2O per mole of H2O. Mole cancels mole. So this is going to give me molecules, but I'm not done because I'm asking how many atoms. How many atoms are in a molecule of water? 3. H2O, 2 H's, 1 O, 3. So my final conversion, I ran out of room. Final conversion is going to be 3 atoms per molecule of H2O. Molecule of H2O, molecule of H2O. Okay, so now we just got to be careful. Notice all the units cancel out beautifully. We're left with just atoms. 2.90 times 1,000 equals, divided by 18.02 equals, times 6.022 E23 equals, times 3, and that's the key at the end, times 3. So I'm looking at 3 sig figs. I'm going to report 2.91. Interesting. It's very close to this. I think that's just a pure coincidence. Yeah, there's no reason it should be the same front number. Just a coincidence. But 2.91 times 10 to the 26th. Now, does that make sense? Of course. Because if you have a big, that's like 10 pounds of water. If you have 10 pounds of water, how many atoms are in that? Well, first of all, there's going to be zillions of water molecules. Each one is 3. So yeah, this number makes sense. And my unit is atoms. All right. Let me see my answer key on that one. Yeah, I think on my answer key, unless I wrote the question wrong here, I put molecules. I don't know if you could see that. So that's actually wrong. I wasn't asking for molecules, I was asking for atoms. So this is what you want to say. Unless I just read the question wrong. Let me see. 13. Yep. This is right. I was wrong before. Okay, next question, 14. The block of ice from question 10, and I believe there was a typo on here because I synthesized two worksheets into one and I forgot the numbering. But anyway, we want to go from question 10. So it's 10 kilograms. It ends up at -6. It's supplied with this much energy. Does it completely melt? So this is going to be another one of those problems where we find the energy and then we subtract it and see how much we have left. Okay. Up, flat, up, flat, up. We're starting with -6 degree ice. The question is, does it completely melt? Meaning, is it going to end up in here or is it going to end up here? So, we don't know. Let's work it out. So the first thing we have to figure out is, of this 2.5 million joules, how many of those joules are going to have to be used up just to take this very heavy block of ice from -6 all the way up to 0? Because remember, it has to go from -6 to 0 before it can start to melt. So, Q equals mc1 delta T. We're finding Q. Q equals my mass. You need to plug in grams here, not kilograms. So it's going to end up being 10,000 grams. C1 is your heat of fusion of, not heat of fusion, specific heat capacity of ice, which is 2.10 joules per gram degree Celsius. And my delta T, we're going from -6 to 0, so that's going to be 6 degrees Celsius. Let's see what we get. 10,000 times 2.10 times 6. That can't be. I guess it looks a little low. Hold on. 10,000 times 2.10 equals times, okay, 126,000 joules. Okay? I guess that makes sense. So, we need to see now how much we have left. So I go 2,500,000 minus that answer gives me 237,400 joules left. 2,374,000 joules left. Okay? So of my original 2.5 million, I made a little crack in that, a little dent in that. All right, so now we're going to see, will it completely melt? So there's actually two ways of going about this. You can say how much heat is required to melt a 10 kilogram sample, and then once you get that, ask yourself, is that more or less than this? Another way of doing it is to say, how much ice can I melt in terms of grams? How many grams of ice could I melt with this much energy? And then say, is that more or less than 10 kilograms? Let's do the second method. So the question I want to ask myself is, if I have this many joules left, how much or what mass of ice can I melt? All right, Q equals MLF, latent heat of fusion, or HF. We're going to solve for mass, because I'm going to say, what mass of ice could this many joules melt? M equals Q over LF, which is 2,374,000 joules divided by latent heat of fusion, which is 334 joules per gram. Joule cancels joule. Gram is the double denominator, or an inverse of an inverse, which comes up at the top. 2,374,000 divided by 334. I messed up a number. Divided by 334 gives me 7,107 grams. Or with three sig figs, I guess I would say 7,110 grams. So what that means is the answer is no. The heat I have left over can only melt 7,000 grams. It can't melt 10,000 grams, which is how much I needed. So that's one way of solving this. The other way would be, how much could I melt with that? In fact, let me do that real quick just so you can see. If I wanted to see how much I could melt with this, the formula is going to end up being 2,500,000. No, sorry, I'm phrasing this wrong. I'm not looking at that. I'm saying how much heat would be required to melt this. So I would take my 10,000 grams and I'd multiply it by 334. And that would give me 3,374,000 340,000 joules. And what that means is I need 3,340,000 joules to melt that block of ice. Do I have that? No, I'm like a million short. So the answer is no, whichever way you look at it. Question 15. All right, looks like a combined gas law problem. So let's write what we're starting with. That's my initial volume. V1 is 840 milliliters. P1 equals 329 mmHg. And T1 is 21 degrees Celsius. But of course, right away, we're going to add 273 and get 294 Kelvin. The volume of the gas is doubled. So another one of these. All right, well, let's double that. So V2 goes from 840 to 1680 milliliters. If I really want to be technical with my 2 sig figs, I'd call it 1700, but we'll deal with sig figs at the end. The temperature is increased to 42 degrees Celsius. Again, it looks like I doubled it, didn't it? But I didn't, because in Celsius, we don't really double it, only in Kelvin. So T2 is going to be 42 plus 273, which is 315. So again, you didn't double it. You went from 294 to 315. So you only increased the heat by a tiny sliver. What's the final pressure? So P1 V1 over T1 equals P2 V2 over T2. What's held constant? Number of particles, nothing else. Let's find the new pressure. So to get P2 by itself, T2 is going to disappear and reappear up here by multiplying it. V2, you're going to divide both sides, so that ends up down here. And that's my formula. Let me just take a quick look at this problem real quick. So you're doubling the volume. What should that do to the pressure? Double the volume, the pressure should cut in half. But you're also apparently doubling the temperature. Now you're not. But if you did, in fact, if you double the temperature, which should double the volume, the two net effects should cancel out and should be the same thing. I think that's kind of, they're trying to trick you here. But it didn't. You doubled the volume, but you only increased the temperature by a sliver. So I'm actually guessing the pressure is going to go way down. Not down by half, but down by maybe 90%. Yeah. Well, it'll be a decrease of 40%. Okay. Let's solve. So P2, so 315 Kelvin is T2. P1 is 329 mmHg. V1, 840 milliliters. V2 is 1680 milliliters. T1 is 294 Kelvin. Let's check our units. Kelvin cancels Kelvin, milliliters cancels milliliters. I'm left with mmHg, which makes sense for pressure. I could leave it in mmHg too, because it doesn't ask the unit. 315 times 329 equals, times 840 equals, divided by 1680 equals, divided by 294 equals 176.25. Now in terms of sig figs, I'm seeing 3, 3, 2, 3, 3, 2 sig figs. That's my limiting. So I'm going to go with 180. Final answer, 180, what's my unit? mmHg. And based on my kind of logic, this makes sense. You're going from 329. If you really cut that truly in half, it'd be about 165. You didn't really cut it truly in half. You cut it in half and then you raised it a sliver. So 180 makes sense. All right, final question. Empirical molecular. So in this problem, I didn't give you a percentage. I gave you the actual grams, which are just the same type of difficulty. All right, 6.12 grams of nitrogen. 24.9 grams of fluorine. What's the empirical formula? And then I tell you the molecular weight and ask what's the molecular. So again, we have to work out the empirical formula first. So I'm given grams. Let's convert these right into moles. All right, 6.19 grams. So nitrogen is 14.01. So 1 mole over 14.01 grams. Let's do the math here real quick. Fluorine is 1 mole over, was it 18.99? Yeah, 19.00. Okay, grams of fluorine, cancel grams of fluorine, grams of nitrogen, cancel grams of nitrogen. Let's see what we get. 6.12 divided by 14.01 gives me 0.437 moles of nitrogen. 24.9 divided by 19.00 gives me 1.31 moles of fluorine. I'm looking for the ratio. Now this looks a lot like 1 to 3 to me, but just to be sure, here's how we check. You pick the smaller number, which is this, and divide both sides by that smaller number. What I'm doing is I'm forcing this to be 1, so that means I'm doing a this to 1 ratio, and I'm hoping for a nice clean whole number. If you don't get a nice clean whole number, well, there's a couple of cases. If you end up with like 2.5 to 1, you would say, well, 2.5, that's just half of 5, so you would double both of them, and again, if you have 2.5 to 1, it would be a 5 to 2 ratio. If you get like 0.3333 and 1, then you triple everything. If you end up with a random number like 0.87, you probably did something wrong. All right, let's see what we get. So this obviously equals 1.00 moles of nitrogen, and this obviously is going to be divided by 0.437, 2.9977, which with 3 sig figs is a nice, clean 3.00 moles of fluorine. So I was right, it's a 1 to 3 ratio. My formula is NF3. Nitrogen trifluoride. But remember, that's just the empirical formula. The molecular might be the same, it might be different. So, to find molecular formula, I look at the molecular weight, also known as molar mass, and that's 142. I need to get this molar mass and compare the two numbers. So nitrogen is 14.01. Each fluorine is 19. So I'm going to multiply or add 3 19s to that. And I end up getting 71.01. So right off the bat, I can see the trend here. 71, 142. It's obviously twice as much. Or in other words, the empirical formula is half as much as the molecular formula. So the molecular formula weighs twice as much. I'm just going to double this. So I get N2F6. Now remember, if this were ionic, this wouldn't be correct. You would always simplify it, but it's not. Non-metal, non-metal, that's going to be your formula. So the empirical formula is nitrogen trifluoride. The molecular formula is dinitrogen hexafluoride. All right, that's it. Good luck.